So we did the Fubini theorem actually.
Yes, sir.
So you're going to have the Fubini theorem here. Okay. So Fubini theorem allowed you to do what? So it allowed you to interpret the double integral actually. Okay. But interpreting the volume integral physically is going to be different, because think about it. What was the interpretation of double integral? The interpretation of double integral was that, okay, if you have a scalar field that you want to integrate, okay, over a region in 2 dimensions, so you're going to say that, okay, take the surface, the graph of that scalar field,
And the heights.
and then the volume under that, what do you call, okay, this surface is really the interpretation of the double integral actually. Okay. The question is, if you want to interpret, for example, if I substitute f here, that would be, so how it was volume actually? So how in 2 dimension, how it was volume? This is important. So why am spending time on this? Just because this is important to make sense that, so we said that f of xy is really like the f of xy is height actually. Okay. So you have this really a small cube, okay, with height f of xy, and the dimensions of the base of the cube is these dx and dy. So f of xy, dx, dy can be interpreted as a small chunk of the volume, really a cube. But the trouble would be if you have now z and dz.
4 dimensions.
So we are in 4 dimension now. Okay. So it would be really a hyper volume actually. Not really a volume, but a hyper volume under this, volume. So it's difficult to really make sense of it. It will make sense more if you have this bounded volume, closed volume. Oh, yes, you can make sense of it. But if you have a generic volume, it's difficult to make sense of it. But so you can interpret it as the hyper volume. So by hyper I mean higher dimension than 3. Okay. So whenever you hear a word hyperplane actually, so for example, what is a one-dimensional plane? So it's a line. The line is a one-dimensional plane. Huh? Okay. So x equal to 1 is a pretty complicated thing if you think from it, because if you are in 2 dimensions, that represents a line. Okay. If you're in 1 dimension, that represents a line. If you're in higher dimension, that represents a plane actually. X equal to 1 is a plane that is attached to it. Think about it. And so this in higher dimension, for example, more than 3 dimensions, you're going to call it as a hyperplane actually. So God knows how does that look like. Okay, but so how do you know that the objects in the hyper dimension, in the higher dimension than 3? Okay, so I know that the shadow of a one-dimensional object is really a point. You take a line actually, think about it, and see its shadow is going to be a point actually.
Yes.
And if you take a 2-dimensional region, okay, and you see its shadow in a line, so it's going to be a line. So if you have a 3-dimensional object, its shadow would be 2-dimensional. Okay? So here's a really interesting thing. So the 4-dimensional object is something whose shadow is 3-dimensional actually. Think about it. What do you mean by having a 3-dimensional shadow of something? It's going to be very interesting to think about it. So you can have a discussion over it. Getting into the head. Even in some senses, we can't picture the 4-dimensional object, but we can picture their cross sections actually. We can picture their cross sections. Okay. It's the analogy really comes from this, what do you call, this Flatlander's novel actually. Flatlander's novel. Think about it. You have these 2-dimensional being living in this plane. Okay. And they have no conception of 3 dimension. Okay. And imagine a cone is passing through it, through this 2-dimensional plane actually. So you have this 2-dimensional object which is looking at it. So when the cone is going to hit 2 dimension, so what he's going to see first?
Circle, sir.
So you're going to see a dot actually.
Yes, sir, first
See a dot.
Then
as the cone passes through, he sees that something miraculous is happening. Santa Maria, huh? It's a point, and the point becomes circle. It becomes circle and circle, more bigger circle, and boom, gone. Okay. So you can just see the cross sections of it. You can just see the cross sections of it, and we can recognize things from cross sections. So if you have, for example, the two-dimensional objects can develop mathematics through which they can talk about the cone. That they haven't seen the cone, but they can talk about the cone actually, because they can say that cone is something whose cross section look like this actually. Are you getting the point? So cube is something whose cross section is. So if for example, if a cube is passing directly through it, so this box is really, for example, passing through two dimensions. So what they can observe? You can observe a rectangle that appears for some time and then goes off. Okay? But yes, it would be interesting if the rectangle passes in this manner actually. In other words, the first hits this border, okay, and then you're gonna see you have a point for which and then becomes a triangle and a bigger triangle and a bigger triangle, and then becomes a quadrilateral, and then again triangle, and the triangle gets smaller and you have a point again actually.
They will be confused.
They'll not be confused. I mean, if they are clever enough, they can build a mathematics. So for example, okay, we haven't seen things in 4 dimensions, but we can we can talk about their cross sections. We can talk about their cross sections. Is it making sense a little bit? Yes. It's okay, so let's out of this philosophical discussion and move to the more stuff. So let me write a Fubini theorem in special Fubini theorem. Special Fubini theorem. So suppose V is Fubini. Okay, so could be type 1, type 2, and so on and so forth. And suppose V is rectifiable. Rectifiable. Okay. Then, and suppose F is okay. So if V is type 1, you can have a similar versions for other types as well, type 1. And F is a map from V into R, is continuous. It's like something that is defined over this.
yes.
So it's really a scalar field, right? It's basically defined over it's continuous. Okay. And then following is true. This guy, you can prove actually that this guy f of xy is z dx dy dz exists. So this exists. So not only this exists, but this is equal to, in other words, you can recover this by doing the double integral. Okay? Doing the double integral of the shadow. So double integral over the shadow of the Fubini type region 1 of what? By integrating this f of xy, dx, for example, dz. Okay? बिल्कुल z आएगा dz and dx dy, where you need to integrate it from this surface phi of xy to the phi 2 of xy.
You're getting the ideas.
सही है
think of it. That's what is basically happening. All right. We can change to the surface integral. We'll see this. We can turn it into the surface integral. And then, I mean, if you are lucky enough, and you are in assumptions of a Stokes theorem, maybe you can turn it into the line integral as well. Okay? It would be the case. For example, if you take the pillow, this will happen actually. Think about it. Think about it. So you have, you have to, for example, compute the volume integral of something. Okay, I'm just giving you a imprecise picture. So I'm going to prove the divergence theorem, okay, which is going to be really interesting. So what was the divergence theorem was doing in in two dimension? So we're saying that if you compute the divergence of what do you call of a vector field in a region, then it is equal to the total f that is exiting through the boundary of the curve in normal direction actually. Okay? So you're going to have a similar three-dimensional version. So what are you going to say? You're going to say that the divergence that is happening in the pillow is equal to of a vector field, something flowing inside the pillow, is going to be equal to the f that is leaving through the surfaces of the pillow. Okay? So you're going to have a surface integral of f through the pillow. And if you are lucky enough, that surface integral can be turned into a line integral, okay, of the common boundary that is really, that is the common boundary of both surfaces. So it's possible, but one thing is for sure that yes, you can turn volume integral into the surface integral. Okay, so we're going to do it. Okay. So let's do one example. So there are some examples. So interpretation of this hypervolume, whatever that means. So it's a hypervolume whose cross sections are three-dimensional volumes. That's what we can make sense of. Because its shadow is going to be three-dimensional. Okay. There is a specific kind of functions in which you can interpret, such kind of functions. Okay. So here's the thing. So take a S that is rectifiable. Take a S that is rectifiable, and take a F that is defined over this S actually. So how does it going to look like? So I am in two dimensions. Maybe this is my S, and so this is a surface, really, which is is right above this surface actually. So this is F of S. Take it. Let V, okay, it's going to be a bit different than this, okay, but almost similar. Let V be a Fubini's type 1 region, okay. So you can have a similar result for other types as well, Fubini types 1 region. The region. So if it is Fubini type 1, you need to tell me the boundary. So the one boundary is this top surface, in other words F and I'm assuming that it's a kind of a volume whose other boundary is this plane actually, x equal to 0. Okay? So I'm conceiving the entire volume between this surface and the plane, okay, the xy plane. So it's a Fubini region with boundaries. So the one of the phi of xy is f. Okay? Okay, so phi of xy is really f of xy. So take this top f as a boundary and take phi 2 of xy as a 0. In other words, take this plane. Okay? Take this plane. So in this situation, okay, in this situation, you may interpret the volume integral because by Fubini theorem, this volume V is going to be f of xy. Okay. So what I would like to do is that really we would like to connect. So we interpreted double integral as of f as the volume under this surface actually. So I would like to recover this fact from this definition actually. So here's the thing. Take the volume of the V. So by definition it is equal to what? That you integrate this dx or maybe dz, dx dy over the V actually. Okay. That's it. Now, like integrating this 1. So is this 1 a continuous map? It's a constant, so it must be a continuous map. So by Fubini's theorem, this must be equal to what? And equal to the surface integral over the S and integrating
0 to f of x.
0 to f of xy what dz
dx or
dx dy. Okay? I'm not integrating f, I'm integrating 1 from 0 to f. That's it. So what would be the output?
So it will be the
Output would be the double integral of f of xy
Fubini theorem.
over dx dy. So it makes sense. Okay? So in other words, if I have a volume, okay, whose top is a surface, okay, and the bottom is really xy plane, okay, then volume of such a region can be found by just computing the double integral of it. Double integral of f over the region S, where S is the shadow of the volume. Are you getting the point? So what does this result is signifying? So this result is signifying that, so we interpreted this as a volume actually. So now we can really see that it is indeed the volume of the field. Okay, so this makes sense. Are you getting the point? It connects the both notion, the volume that we studied previously with the volume that we are talking about now. Okay, so it works for a good number of surfaces actually, okay, which are Fubini type 1 and Fubini type 2 or Fubini type 3. The only thing is the order of integration would change, the rest is same actually. So what is the benefit of this formula?
Sir,
जी
यहाँ पे फंक्शन को 1 क्यों रख रहे हैं सर?
कहाँ पर?
f of x y.
नहीं ये तो हमने डिफाइन किया था, याद है? What was the definition of a rectifiable volume? So we said that the definition of a rectifiable volume is this triple integral. Okay? That you take this volume, fill it with the cube and sum up all the volumes of the cube section. Okay, that would be equal to the volume of, and this should be finite. Okay, so that's how we define the volume. Okay. So let's compute. So we take one example. So we did this example of a rectangular region actually. So let's compute. So imagine that you have this rectangular region. Okay. Say with vertices A 0 0. For example 0 A 0 and 0 0 A. Okay. Will make it sense? And so you have this plane, okay, and so the volume under this plane, I'm calling this V. Okay, so the V is the volume under the rectangle. Can you picture this? Can you picture this picture actually? So if you take a rectangular region and put it in a corner actually, okay, that's what really it means. Okay. So here is the challenge. Prove that this volume of V is really the 1/6 of the volume of the cube that has dimension A, and A actually. So what would be the volume of 1/6 of the volume of cube? So that's what we would like to verify, that the volume of this region is really the 1/6 of the volume of the cube. Okay? What should be the first thing? The first thing should be that you can treat this as really okay. You can treat this as a diamond, or what should be the proper name for it? What would be the shadow of this in XY plane actually? Because the first thing, if you want to compute the volume, you need to compute the volume in this manner actually. Okay, you need to compute this volume. So you need to identify first few things actually. So what is your S? So what would be the shadow of this in the two-dimensional?
Triangle.
This is going to be a triangle. So the first thing is that it's going to be a triangle in XY plane that passes through A 0 0 and 0 A 0 actually. So this will be a triangle actually. Okay. So this is my A. What should be the equation of this line?
X plus y.
X plus y equal to A. So it's going to be X plus y equal to A. X plus y equal to A. Okay? What is the other thing? The other thing is that you need F that is defined over S actually. So what I want to do is that I want to see this volume as, you know, area or the volume between the XY plane, okay, and this surface actually.
Yes.
Okay. So with this recipe, this plane is going to play the role of the F actually, what you have there. Okay. So this is going to play the role of the F. So what would be the equation of this?
X plus y.
So this is going to be X plus Y plus Z equal to A.
Yes.
And
So what would be the F of X, Y?
so it will be a minus x minus y,
So it's going to be A minus X
X
minus
minus
Y.
y.
and then we will put in.
And then you can say that the volume V can be treated as the triple integral of this V over dx, or maybe dz, dx, dy. Okay? And by Fubini theorem, so there is nothing wrong, you know, this guy is continuous. Okay? This guy is continuous. So there is nothing, we are in the assumptions of Fubini theorem. So what you can do, this is going to be equal to the double integral over S
And 0 to f,
of the integral that goes from 0
to f of x
to
y,
a minus x minus y
1 of d,
and dz over
dx.
dx.
And so what are limits of dx and dy?
आते हैं वो कौन सा मुश्किल है? Just think about the triangle. So what would be this? So this A is going to be the double integral of a minus x minus y and dx dy. Okay? And the x goes from where to where? So x always goes from 0 to this above line. Hey,
Yes, sir.
I should go this way. So x always go from this to this line. Okay? So what limit you should put?
So, a minus 0.
0 to a minus y, while the y goes from 0 to 2. So just solve this integral. And once you're going to solve this integral, you're going to get a cube over 6. Is it making sense? Okay. So that's also Fubini type 1 region. Though you can treat this region any Fubini type. Think about it. So I can take its projection on YZ plane. So it's going to have a triangle here.
ZX plane.
ZX plane. So it's all three diagonal ones. Is it making sense?
Yes, sir.
एक और छोटा सा एग्जांपल करते हैं. So here's another example that we can do. So let's have this parabolic bowl v equal to x square plus y square. So what would be the picture of this? And
Parabola
z equal to x square. Z is going to be always positive. It can't be negative actually for sure. So it's going to be above. So how does it going to look like?
bowl.
So at z equal to 0, so it's going to be 0. So you can see that different cross sections, and you can see that it's going to be a bowl. Okay, up to the height h actually. So it goes up to the height h. Okay, so you have this. So this guy, so this height is h. Okay, this height is h. And by h, I mean that the z is between 0 and h. That's what I'm saying. The z is between 0 and h. Okay? And okay. So it says that imagine you have this bowl and you fill this bowl with a gas actually. Some kind of a gas. Okay? So you fill it with some kind of gas. And we have been asked to compute the mass of that gas. So how much stuff, okay, how much mass of this gas this bowl contains actually. One information is given to me, and that information is, okay, so another information is given to me is that the density of the mass, okay, the density of the mass density is proportional to the distance from the z-axis actually. Okay, filled with the height as gas cloud whose mass density is proportional to distance from the z-axis. Okay, so in other words, the z. So if I, for example, if I take, so if I take, for example, one arbitrary point in the bowl, okay, and I want to know what is the density of the gas at an arbitrary point in the bowl, I'm going to say that you just have to know that how much it is away from the z-axis. Okay, so this is it. So this rho is proportional to the how much that point at which you want to find the mass is away from the z.
Distance away from z.
Yes. So I would like to, I'm going to write an expression for it as well soon. So the question is, what is the total mass of gas inside this volume V? ठीक है? Inside this volume V. What is the type of the volume?